Students, good morning. Today I am going to discuss about the Carnot cycle. Carnot cycle. About Carnot cycle, construction of Carnot engine, assumption involved in Carnot engine construction, and Carnot theorem. This is part 1. This is part 1. Due to time availability, more than 12 minutes, there is a problem in uploading the video in YouTube. Hence, I split up into 6 parts. Part 2 is reversible isothermal expansion. Part 3, reversible adiabatic expansion. Part 4, reversible isothermal compression. And part 5 is reversible adiabatic compression. And part 6 is efficiency of a Carnot engine. First, Carnot cycle. Carnot cycle is a hypothetical cycle. Hypothetical cycle. Hypothetical cycle. In real-time process, it is difficult to construct this Carnot cycle because this is an ideal reversible cycle. Ideal reversible cycle. Third point, it is standard of perfection. Standard of perfection. Okay, this cycle is used to compare the efficiency of engine working in real-time condition. Clear? Carnot cycle is a hypothetical cycle. It is impossible to construct because it is an ideal reversible cycle. Moreover, Carnot cycle acts as a standard of perfection used to find or compare the efficiency of an engine working in real-time condition. Okay, this is Carnot cycle. Next one is Carnot engine. Carnot engine. In our discussion, a piston cylinder arrangement is a Carnot engine. Is assumed to be a Carnot engine. This is cylinder. This is piston. Piston cylinder arrangement. Piston cylinder arrangement is a Carnot engine. In this engine, ideal gas is taken for consideration. I am taking 1 mole of an ideal gas. 1 mole of an ideal gas. Since n is equal to 1, hereafter our calculation PV is equal to RMTT. This is Carnot engine. What are all the assumptions involved in this Carnot engine? There are 6 assumptions. One is piston moving in the cylinder up and down direction. Piston moving in the cylinder will not produce any friction during its movement. No friction. 100% frictionless experiment. Frictionless. 100% frictionless. The piston moving in the cylinder will not produce any friction at any cost. Assumption 1. Assumption 2. The walls of the piston as well as cylinder. Walls of piston is assumed as perfect insulator. This is assumption 2. Assumption number 3. The cylinder head. This is called a cylinder head. The cylinder head is designed to act either as a perfect insulator or act as a perfect conductor. Okay, this is assumption number 3. Assumption number 4. During the cycle certain amount of heat is transferred from source to engine. Similarly, certain amount of heat is transferred from engine to sink. During this heat energy transformation, the temperature of source as well as sink is constant. There is no changes in temperature of the source. That means hot thermal reservoir. Temperature is constant. Temperature is constant in hot thermal reservoir source as well as cold thermal reservoir sink during the energy transformation, heat energy transformation from source to engine. Similarly, engine to sink. At any cost, the temperature of source as well as sink will not be changed. Temperature is constant. This is assumption 4. Assumption 5. The working fluid used to transfer heat from source to engine, similarly engine to sink, is a perfect gas. Is a perfect gas. Perfect gas. Constant heat capacity. Constant heat capacity. Constant heat capacity. This is assumption 5. Assumption 6. Assumption 6. In Carnot cycle, we have two processes. One is expansion as well as compression. One is expansion, one more is compression. Both expansion as well as expansion and compression are highly reversible. Here there are 6 assumptions. One is no friction. During the movement of piston in a cylinder, it will not produce any friction. Second assumption, walls of the cylinder as well as piston will be a perfect insulator. Third assumption, the cylinder head is designed to act either as a perfect insulator or as a perfect conductor during the transformation of heat from source to sink, source to engine as well as engine to sink. Fourth assumption, temperature is constant during the transformation of heat from source to engine. Similarly, during the transformation of heat energy from engine to sink, temperature of source as well as sink is perfectly constant. Next, the working fluid used to transfer energy from source to engine, similarly engine to sink, will be a perfect gas, constant heat capacity. And 6, both compression as well as expansion process are highly reversible. These are all the assumptions. Next, Carnot theorem. Carnot theorem. Theorem number 1. Carnot theorem. Theorem number 1. Engine, this heat engine acting between two thermal reservoir, hot thermal reservoir as well as cold thermal reservoir. This is source, this is sink. Okay, this is sink. The Carnot theorem says that any engine working between hot thermal reservoir to cold thermal reservoir, any engine acting between hot thermal reservoir as well as cold thermal reservoir, its efficiency is always less than that of efficiency of the heat engine between thermal reservoir at constant temperature. This is called as pH. This is called as PL. pH is constant. Similarly, PL is constant. Any engine working between two thermal reservoir at constant temperature, its efficiency is always less than that of efficiency of the reversible engine. Clear? This is theorem 1. Theorem 2, efficiency of the heat engine. Efficiency of the heat engine depends on temperature of source as well as temperature of sink. The efficiency of the heat engine depends only on temperature of source as well as temperature of sink. It does not depend on the temperature or nature of the working fluid. It does not depend on nature of the working fluid. These are all the two theorems. In part 1, we discussed about Carnot cycle, Carnot engine, construction of Carnot engine, what are all the assumptions involved in Carnot engine during the operation, and Carnot theorem. Next, part 2. In part 2, we have 4 classification. Part 2, reversible isothermal expansion process. Okay, students, I request you all to continue all the 6 parts. Thank you.